Hi everyone, we are a team from bioengineering and we're excited to show you our work. My name is Kate.
My name is Nick.
My name is Carol.
And my name is Jackie.
And today we present Medisign, which is a two-way interface to improve communication between deaf patients and hearing medical professionals. In the US, there are up to 1 million American Sign Language, or ASL users, and with only 70,000 interpreters, communication can be a major challenge. One of the most important conversations you can have is with your doctor, and typically an ASL interpreter is present to facilitate this communication. However, due to the low supply and high demand for these interpreters, the availability of this service can be limited. Next, you might be wondering, what about passing notes? This is a common misconception that people have about the deaf population, and in reality, there are fundamental problems with this approach. Ultimately, American Sign Language is not the same thing as signed English. The two languages have distinct grammar, vocabulary, expressions, and even medical terminology. There's a study that shows that trying to use written English to communicate with a Spanish speaker versus an ASL user is actually more effective with a Spanish speaker. So to recap, we have these limitations of interpreters and written English. And some consequences of these limitations include delayed appointments and miscommunication, which ultimately can contribute to misdiagnosis and mistreatment. There's a study that shows that only about 2% of deaf patients have appropriate access to the diagnosis of mental illnesses. This shows some quotes from deaf patients showing the frustration of not having an interpreter, especially in the emergency setting, which can be very distressing and alienating. To bridge this gap, we propose Medisign, which enables deaf patients to use ASL and hearing medical professionals to use spoken English to enable these very important conversations. Looking at the current solutions, there are a few requirements for a successful device, including ASL input, which allows the patient to sign into the device, ASL output, which allows the patient to see the response in ASL, facial expression, which is very important for ASL meaning, and lastly, medical relevance for this particular setting. This slide shows the importance of facial expression. As you can see in the two videos, the same hand shape to understand can mean on the left, yes, I do understand, and on the right, no, I don't understand, all depending on the eyebrows, the mouth shape, and the head movement, and it's very important to distinguish between these two. Overall, our device is innovative for its ASL input and output, its analysis of facial expression, and its medical relevance. And now I will pass it on to Nick to discuss our design goals.
Thank you, Kate. So after talking with stakeholders, we came up with 4 major design goals. They are portability, to ensure that our setup is easily maneuverable in a hospital setting, usability, so that both doctors and patients can intuitively operate our interface and maintain conversational flow, cost effectiveness, to minimize the financial burden on healthcare providers, and most importantly, translational accuracy, to ensure that the translated messages are correct. The accumulation of these 4 design goals, along with physical hardware, open source algorithms, and our own code, accumulates to form Medisign, a comprehensive two-way communication interface between English and American Sign Language. But how exactly does Medisign go back and forth between ASL and English? I will first take you through the top pathway from English to American Sign Language. First, a doctor will speak into a microphone, and that speech is transcribed into a string of text. Then, neural-machine translation will convert that text into a list of ASL gloss terms. ASL gloss is the written depiction of American Sign Language. Finally, the list of ASL gloss terms is parsed for individual signs, and signing videos are queued for the patient's viewing. In the event that a video is not present in our library, our algorithm will default to finger spelling, where each letter of the word is signed individually.
So now that Nick has shown you how our device translates English into ASL, let's see how Medisign handles translating American Sign Language into English. The process starts off with a deaf patient signing directly in front of a motion capture device from Microsoft called the Kinect. The Kinect allows us to track multiple points on the body and their position in space through time. For the purpose of Medisign, we track the head, the torso, both elbows, both hands, and multiple points on the face in order to ensure that our algorithm includes facial expressions. So as we track these points on the body, we extract their XYZ coordinates, normalize them, and store them in a 3D matrix, which represents the deaf patient's ASL input. We then take this 3D matrix and compare it to a library of stored sign matrices of the same form, one by one using an algorithm called dynamic time warping. DTW for short. DTW is an algorithm that is mostly used to compare the similarity between two temporal sequences. As a result, this allows us to classify the deaf patient ASL input as a specific sign or series of signs, depending on which signs in our library are most similar to it. Once classified, we take the ASL gloss representation of the deaf patient ASL input and translate it into English using neural machine translation. And finally, we output the fully translated English as audio so that the doctor can hear it. So now we've shown you how Medisign is capable of this two-way communication between a deaf patient and a hearing medical professional. So let's see it work. This is our user interface. On the left-hand side, you see the video input from the Connect. In order to begin the process of translating ASL, the deaf patient has to put one of their hands into the green box, wait for the countdown, which is shown in ASL, begin their signing, and once they are done, they put their other hand into the red box. The system then translates it and outputs the audio. On the right-hand side, you see the hourglass image. This is a placeholder for where the ASL videos will be shown once English to ASL translation is complete. The two buttons below it allow for the doctor to start and stop speech acquisition for English to ASL translation. And now we will show a video of what a very, very short conversation between a deaf patient and a hearing medical professional would look like with Medisign. Just a disclaimer, we have edited out the delays due to long translation time, but we will discuss that further later on. And now, Medisign. So as you can see, Jackie here, the deaf patient, begins the ASL translation process. She waits for the countdown and then signs, "My head pain," or in English, "My head hurts." She stops the acquisition of the ASL.
"My head hurts."
And translation occurs. The doctor now responds,
"Take the medicine once a day."
He stops the speech acquisition, and the videos of ASL are displayed for the patient to see. And with that, the conversation ends.
Thanks, Carol. As we've seen in the video, we want our final product to meet 4 main design goals. It must be portable, usable, cost-effective, and accurate. So let's see how Medisign stacks up. First, we looked at portability, as in the size and weight of our device. It fits through a standard hospital doorway, and it's light enough so that it's well under the recommended 35-pound limit that a nurse can safely lift. Next, we evaluated usability, as in the translation and initialization time. Initialization of our device is extremely fast, so that it would not cut into a standard 30 to 45-minute doctor's appointment. However, translation time is much slower, hovering around 15 to 20 seconds. We have recommendations in the future for how we could effectively drop down this translation time. First, we will convert the algorithm from MATLAB, a language with a large computational overhead, to something like C++, which traditionally runs much faster. Additionally, we currently do a linear search in our library of ASL videos. However, if we were to switch this to a binary search, we could cut down the time to find and display an ASL video to a much faster time. Next, we looked at the cost effectiveness of our solution. We wanted to see how it stacks up to an ASL interpreter, which currently start at around $100 an hour. The sum of all of the components of our device come to around $300, meaning that this would be a great investment for a hospital or insurance company, as the device would pay for itself in just 3 hours of use. Additionally, if we were to purchase some of the components of the device in bulk, we may be able to drop the price even further. Finally, we wanted to look at the translational accuracy of our device. We evaluated the accuracy by taking a weighted average of the number of words translated correctly, as well as the number of words translated in the correct grammatical ordering. However, our translational accuracy was not as good as we hoped, between 45 and 57%. However, what does an accuracy of 50% really mean for our device? Well, it means that a sentence like, "When was the last time you saw a doctor?" would actually be translated into, "When be last time you see doctor?" This is not correct ASL output. However, some of the parts of the message do get conveyed. We weren't satisfied with this, and we wanted to see what was really driving our accuracy down. In the machine learning world, you must train your machine learning model on something called a corpus, or a known body of text. A small corpus is on the order of around 1 million sentences. But since ASL is not a typically written language, we worked with what we could find, including part of a standard corpus from a collaborator, a curated body of song lyrics, and some hand-translated fictitious medical conversations to give the corpus specificity. We believe that if we were able to increase the number of sentences in our corpus, we could effectively increase the translational accuracy of our device.
So moving forward, the biggest priority for us is to increase translational accuracy. And as Jackie mentioned, the way to go about that is to make a more robust corpus. Additional lines of future work include supporting more than 2 conversation participants, tailoring our corpus to account for other medical settings like pharmacies or emergency rooms, and integrating finger-spelling input into the ASL to English translational pathway. In summary, we believe that Medisign provides a framework for effective two-way communication between English and American Sign Language. And with some improvements, we're confident that Medisign can bridge the gap between the hearing and signing world in a medical setting. And with that, we'd all like to say thank you, and we're happy to take your questions.
Is the issue of accuracy an issue of the corpus, or is it an issue of calibration? In other words, people sign somewhat differently, and how the machine recognizes that sign might misinterpret it in different sentences. Does it make sense to try to recalibrate when you have patients do certain signs in order for the machine to understand what those signs are, or letters, in order to kind of go from there?
That's a great question. So I brought up the breakdowns of the different parts of the pathway, and you can see the text to ASL gloss and ASL gloss to text are the 2 parts that rely on the corpus, and those are the ones with the lowest accuracy, but I believe Carol also has an answer for this.
Yes, so what we did not mention is we actually had in mind to have a calibration process where we asked a user to sign 5 to 10 signs and see what the average rate of their signing is, so that when we do acquire their ASL, we're able to break it down in specific chunks so that we're acquiring an individual sign in the proper order rather than overlaying the signs. The other thing is dynamic time warping is a beautiful algorithm because it doesn't depend on the speed of signing. That's what the purpose of the algorithm is. So you can take like the sign thank you like this very fast or very slow. And if we compare it using dynamic time warping, that will give us still the same similarity.
Yes.
So this always applies to people conversing with the doctor or physician in spoken language, but when the translation comes back from the doctor to ASL to the patient, how do you know the patient is really understood, irregardless of the actual translation accuracy as you're receiving, you're suggesting? How do you know that they really understood? Now that's maybe a problem we have in English as well, right?
You guys want to answer that?
Sure. Yeah, I guess that we don't have something in place for that right now, but potentially we could have the user sign what they believe to be, the translation, and then our device could then translate it back into English and see if the doctor was actually saying
The reason I'm asking the question is that I think it's a perceived risk. I mean, in
Yes.
spoken language, you just assume you get.
Right.
But here, in terms of adoption, this would be a perceived risk, and I think it needs to be considered.
That's great, yes.
Thank you. Yes.
Very good, but why did you limit yourself to a medical setting?
8.
Yeah, I guess we focus on the medical setting because we really wanted to hone in on the idea of bioengineering and trying to solve a medical problem, but I think this could be applicable to any other setting.
And we also wanted to focus on a setting where this could be a life or death situation, where if there's been situations where you can't get an interpreter for days even, and these patients are left alone. So in that case, our device would be a way to help this patient actually communicate their needs. So yeah, that was why we focused on it.
Thank you.
You're hung up on the accuracy, understandable, 50%, 60%, you're not close to that. Is there some sort of benchmark that how good is good enough? So you may not need 100% for people to understand.
Yeah, so it's actually been shown in the machine learning world that an accuracy of around 95% is the threshold for human understanding. So if a sentence is 95% accurate, a person is able to fully understand the meaning of it most of the time, I think, or a majority of the time.
Is there any way to characterize when something is wrong, what is wrong? Like, take the medicine once a day versus take the medicine once a week? That is an area that's really, I could imagine it's really bad, but if it's something else that's a lot smaller, it's like it wouldn't make much of a difference. Is that something that's taken into account when measuring that stuff?
In our device as it is now, I don't think it hasn't been addressed, but potentially we could have in the GUI, maybe the physician can press a button that says week or something like that rather than day. If the system knows you're saying, oh, take something this number of times. You could say, have a button that says day, week, month, or something like that.
And also, as we look to expand our corpus, one of the things that you can do to make sure that the accuracy is met there is include many sentences of that form to make sure that it will always get translated correctly.
And from a GUI perspective, we can always install feedback so the doctor knows exactly what is going to be conveyed before the actual signing videos are played, just to confirm in the event that it's something that was misconstrued, they can re-speak the phrase.
Yep.
Show the text on the screen as you're parsing it, so that even though, as you said, the text is optimal, people can at least use it drawing.
Yeah, it's definitely a great idea for, again, confirming that the doctor knows exactly what is being translated to the deaf patient. Additionally, it is good confirmation as well.
Also, in the case that the deaf patient wants to look over and confirm in written English, if that's what they choose to do, then that's a great alternative.
Thank you very much.
Thank you, guys.
Thank you.